All right. So, hi everyone. Good morning, good afternoon, good evening. This video, I would like to continue our topic on the discrete systems. Now, after analyzing the discrete system in terms of difference equation and maybe a little bit of stability, I think it's time that we consider frequency-based analysis in the form of Fourier series and later Fourier transform, then also Z transform. Okay, so this one, I believe you have studied this in the beginning of this course for the continuous time system. So as you can see, it's not that much different from the continuous time system. It's considered as a parallel of the continuous time system, continuous time Fourier series, and later also Fourier transform. And yeah, the idea is that we do analysis based on the frequency, which means that we basically break the signal down into several frequencies. And there are some differences for the continuous time and discrete time. Especially in discrete time, we can represent the signal as the sequence instead of just the function. We of course can still represent the signal as a function, but I think it's also possible to do that with a sequence. So yeah, the purpose of having discrete Fourier series here is yeah, the basic idea is to ease the analysis of systems with periodic inputs, and the signals here for the periodic inputs, the signal could be represented by the summation of the complex exponential signals. And here the discrete time signal, it is called a periodic signal with period n. So the period here is n if xn, small n, equals to x small n plus capital N. And one example of set of discrete exponential complex signals with a period of capital N is the psi k of n, which is the complex exponential given period, of course, n, large n. Small n is the time or the shift, the running time of the running shift. And here exponential of gk times 2 pi of a large n, where k here is 0 and 1 and 2 and so on. And the difference between the continuous and discrete complex exponential signals is that for continuous signals, we have the period could be any period, so which means that as long as it is positive and it is like a real number, we can handle that. But for discrete, of course, we have to obey the fact or the condition that the period they have to be integer. So if they are integer, then we have several limitations or maybe several differences from the analysis viewpoint. So here we are going to talk about the linear combination of pi k. So if I have the discrete complex exponential signals with frequency multiple of 2 pi, they are considered identical signal. So e to the power of j, here we have omega, large omega plus 2 pi r times n, which is e to the power of j omega n times e to the power of j 2 pi rn. This is the same. Okay, so if I have something here related to 2 pi, let's say 2 pi or 4 pi and so on, they are considered to be identical signal. And this form of the signal, so this is the discrete exponential complex signal psi k, and here they are the same as psi of k plus m n, large n of the time n. Okay. And then representation of xn in the form of linear combination of sequence phi k n, the signal xn. So this is the discrete signal that we have. Xn could be represented by the summation of um, the psi n, which is the linear combination that we have here of the exponential signal. So this is the um, ak times e to the power of j k times 2 pi over n times n. And then since different sequence, this only is for k, then we have n times of the summation. So note that this is summed over k. So if we have a k, times e to the power of j k and so on, we replace k with some value. And since the signal is periodic, so we sum this value only over n, over capital N. So k here is from basically 0 to n, or from n plus 1 to 2n, and so on. So we sum this n times. Basically, we change the limit of the summation, or the length of the summation. And now we could represent this by the Fourier series coefficient, AK. So AK here is the Fourier series coefficient for exponential signals. So now we have, after we obtain the sequence of the signal xn, which is consisting of the multiplication between a k times the complex exponential value. Now we can get the discrete Fourier series coefficient ak, which could be obtained by solving this. Yeah, so basically we get this x n minus 1. We get this, we solve this from 0 to n minus 1, and we can actually obtain the coefficient ak to represent the signal in a closed form as a sequence xn. Xn here, we can represent this as the sum of the signal alpha to the power of n, where n begins from 0 and ends at n minus 1. So this is the closed form closed form representation, and this is the one that I think we have talked about a little bit in the class. So if this is one, then we basically have n, because this would be summed or added n times. And if this is not one, we can make like this geometric sum, uh, where we have 1 minus alpha to the power of n over 1 minus alpha. Thus, this value e to the power of jk times 2 pi over n is 1 if and only if we have k equals 0, and then plus minus n, and then plus minus 2n, where we have e to the power of jk um, times 2 pi over n times n. This would be n if this is, if k is n, so that we can get rid of this n. So everything we have here is in terms of 2 pi. So this would be 1, right? So this is because if we have e to the power of jk 2 pi over n, we have like the trigonometric function of this, right? So this would be, let's say I have e to the power of let's say k is n, then we have e to the power of 2 pi j, and this will be like cos, um, 2 pi plus j sine of 2 pi, which is 1, right? So similar, if we have the signal with k equals 2n and so on, so this would be 1. And if we have 1 here, we sum all of this would be n. Otherwise, we have the 1 minus e to the power of k 2 pi over n times n. So this would be in case of we have the this is not 1, right? So this is not 1, n is not in the period. We have this representation. And yeah, since this is 1, right? For this part here, this is from the same reason, this would be 1, so this 1 would be 0. And for periodic signals, we end up having this. So for k here is in n, right? So from k equals 0 until n minus 1, e to the power of jk 2 pi over n times n. It would be n for k in the period and 0 for others, right? So now we can have this. And if we multiply here both sides in this equation, this would be we having only n equals n here, or this is the range, right? So it means that from 0 to n minus 1, and if we multiply this by this value of jr times 2 pi over capital N times n, we get like this is a sum of xn, which is this. So this is multiplied by this, and now we can have this, and this is the separation between the summation of the AK, which becomes the outer summation, and this becomes the inner summation. And if we have R equals K here of the outer part summation, then here the inner side or inner part of the summation, this becomes N. So this becomes N and 0 otherwise. So if for the same reason, if K equals R, if k equals r here, this means that this is becoming 0, right? But if it's not, then we will have like e to the power of j something. Yeah, so this is some value, and then this is multiplied by 2 pi over n times n. So this becomes 0 if k is not the same as r. So this summation now e to the power of j times uh, k minus r times 2 pi over n times n. This becomes n times delta of time k minus r minus mn. So this means that the value of the summation here is n if k equals to r plus mn, right? Otherwise, if we have time, k equals k equals r plus mn. That would be that would mean that delta here becomes 1 because the time is 0, and this means that the summation becomes n. All right, so from that, now we can get xn, uh, which is now the summation of ak, yeah, the summation of ak times e to the power of jk 2 pi of n. Now this 2 pi over n, this could be omega. So omega here is clearly yeah, it's clearly the 2 pi over n, right? And then we can get an here since we are looking at uh, over one period. So from 0 to n minus 1, which means that we can now divide this by n. So this is 1 over n. Uh, so sum of the x n e to the power of minus jk 2 pi over n times n, which now we again go back to this and we get omega just as a simplification of 2 pi over n. Now, yeah, we have ak. This is called the Fourier series coefficient. So Fourier series coefficient, which is yeah, sum of the value of the signals times the e to the power of, yeah, the exponential complex value, exponential complex part of the signal. So now we can look at this and say, well, if we have the discrete signals, we in this case we still have e to the power of this minus jk, right? Because this is complex exponential. So even though in the differential equation we do not have the um, like exponential term. Instead, we have like let's say like alpha to the power of n instead of the e power of t, for example. But for the Fourier, we still have the coefficient for the complex exponential. So that's maybe just a slight difference. Now, we obtain all of this. So we obtain that xn now is the summation of the complex exponential value of the a0 until a n minus 1. And also we can actually having some shift. So the um, order here, it does not really matter. So the shift here is if we start from 0, well, we can start from 0. If we start from 1, we can end at the different place, but it's not really a problem because later we will have like the same period, and we have the same sequence even though we start at different place. And for phi 0 equals to phi n, now we have ak here equals to ak plus n. So this is the periodic property for the Fourier series. And if k is not less than n, then here the values will be repeated periodically with the period n. So big N, capital N, and the discrete time Fourier series, they only have this n exponential complex term because they are periodic, of course. So we are a little bit limited in terms of the number of terms that we have, which is good because we do not need to look at the um, like an infinite value of like a complex exponential, but instead we have only n values of complex exponential. Okay, so yeah, that's about some backgrounds and maybe a little bit of fundamentals of the Fourier series. So I think we will just go straight into some examples. Here we can see that this is the periodic signal, all right, the discrete time periodic signal. And we obtain here the Fourier coefficient of the signal below. So we have a periodic signal and we are asked to obtain the Fourier coefficient. And this signal, we have to interpret this graph, right? So this graph here we have like, let's say 0, 1, 2, and 1, right? So this part here is periodic and it's clearly let's say it starts at 0 and it ends at 3. So this is the value, and period of course is 4. And if we have the signal with period 4, we can just plug in this value of 4, or 2 pi over 4. Yeah, the period here is n, large n again, and we get the e to the minus j pi over 2, which is minus j. So yeah, this is from again the cos, right? Cos minus pi over 2. Uh, yes, this is minus pi over 2. And this is the minus the sine of j sine, yeah, j sine pi over 2. Sorry, this is not minus. Right, so pi over 2 is 90 degree, right? So this would be like 0, and this would be minus j. So sine of 90 degree is 1, so this would be minus j, sorry. Okay, so we can now get the simplified value that if we have e to the power of minus j pi over 2, it is basically the same as minus j. So this will be helpful to us, right, to get the simplified value, because sometimes the notation could be overwhelming, and there are like many notations that you have to take care of and you have to remember. And to simplify, I think it's nice to get some characteristics here for complex exponential, which we can change into like the rectangular representation of the complex numbers. So now, so if we remember the complex or the Fourier coefficient is done by just plugging on this value. So a to the power, or ak here is just 1 over n. Sum of the xn minus xn times e to the power of minus jk omega n, right? So e to the power of minus jk omega we have to take care of, which is this, right? So this is basically yeah, this part, and we just need n now. So n, of course, we need the k here. K is the uh, moving part, which is yeah, just uh, 1 basically. And yeah, so we can compute A0, we can compute A1, we can compute A2, we can compute A3, and A4 would be the same as A0, and we can also get the characteristics of the next, let's say the next repeated sequence of the signal, which is the same as the previous sequence of the signal. So here we see that A0 here is 1/4 times the summation of xn. So this is actually like xn, yeah, xn times minus j, because we have minus j in the previous slide, yeah, in here. But now we have minus j to the power of n. So this means that or minus j to the power of kn, right? So kn here is so k is 0. So 0 times everything is 0. So we have this 0. So this would be xn. Yeah, xn times minus j, right? Uh, yeah, sorry, it should be 1. Yeah, 1, which is just xn, right? So we have that value of 0, 1 to 1. We just plug in those values, and that's divided by the um, yeah the period 4, or multiplied by 1/4. So here a0 is 1. How about a1? So a1 here we have xn uh, times minus j to uh, the power of k plus n, or k times n, sorry. So k is 1 times n is the running part, right? So xn, yeah, xn times minus j to the, of course, n. So, for example, if we have one fourth, times xn is 0, so we don't need to worry because this is, of course, already 0. But for this, so this would be, for example, 1. So this would be, for example, 1 times like 1 times minus j to the power of 1, which is minus j. So this would be like minus j or minus j1. See that? That's yeah, the same. So for 2 here, we get like a 2 times minus j to the power of 2, which is the, so if yeah, you're familiar with the imaginary number. So if we have a minus j, if so this is basically minus square root of 1. Oh, sorry, square root of minus 1. Uh, then if you have like a minus j, or you have j square, so this would be minus 1, right? If you have let's say minus or minus like a j square, so this would be yeah, this would be 1, right? So j square here is minus 1, and yeah, if you have like minus j square, but yeah, this is not what happened here. So what happened is minus j square. So you square the minus j. So if you have minus j square, it's basically minus j times minus j, which is the same as j square. This is also minus 1. Okay. So yeah, that would be minus 2. And for the fourth term, we have like a minus j to the power of 3, right? Since it starts at 0, so minus j to the power of 3, it's like a minus j of 3 is like a minus j square, right? Times minus j, something like that, which is so this part is 1 or minus 1. Yeah, so minus 1 times minus j, which is just j. So that would be like just j1, and so on. The next part will follow. So now we have A2, we have A0, we have A1, we have A2, and we have A3. So A2 here is that, yeah, we basically plug in these numbers and we get a minus j to the power of 2n. And for A3, we have minus j to the power of 3n. Okay. Now, if we want to draw or to have like the plot, right, the spectrum um, of the frequency based signal, we can have like a AK here, which is 1 for frequency 0, and A1 here is minus 1 for the frequency 1. uh, Sorry, minus half. A2 is 0 and A3 is minus half, and so on. So now we can get the frequency um, part of the or frequency plot, yeah, magnitude plot and phase plot of the Fourier series here. Okay, now another example here is that we are interested to find the Fourier series coefficient of the signal. So this one, it's not in the form of the different sequence, but well, it's in the form, well, it's the same, but now we can get some patterns, right? So the patterns is for time 0 to 2, there is a value. For time 3 and 4, there is no value. Okay, so for time 3 and 4, we can just get rid of this. It's not relevant. But for time 0, 1, and 2, we have to, find the value, which may be a little bit tricky if we have the e to the power of minus jk 2 pi over 5. So 2 pi over 5 is not as easy as, let's say, 2 pi over 4, because for 2 pi over 4, we can simplify this into pi over 2, and we can see that it becomes minus j. But now we have this difference, and we have to work with this with yeah, by doing some geometric sum. So here the first part, it's basically e to the power of 0, which is 1, and the second part is indeed 1. So the this part here is basically 2 plus yeah, 2 plus 1, right? So that would be, we can see that that's, if this is like a, for example, if this is like a, this is the a to the power of, um, yeah, 2 plus 1, right? So that's a power of 3, where if you basically multiply that with this 2 pi, that becomes 6 pi over 5. Okay, then yeah, we can. This is just basically the breakdown. So actually, you can finish here, but to find some like a meaningful value, one way is basically to multiply this by, let's say, by 1, to get the value that may be more representative, to get the to get uh, the value to be able to be computed, right? So I think that's also important. All right. So yeah, now we find the coefficient of Fourier. Okay, I think if this is just 4, that would be very easy. Maybe you can try later in the exercise. So the third example here, still for the Fourier coefficient. Let me pause it. All right, so we continue into our next example. So this is example 3. So suppose that we have the sequence. Now, this is in form of unit impulse. Unit impulse delta, but now it's delta n minus 3k. That would be, so it has a value if the n is 3k, right? Or it has a value if this is like the multiply of 3, right? So if we plot xn, so xn here, n is the time, right? So is the time. K here is from minus infinity to infinity. So if n here is like, let's say, -7, so it does not really have any value. Yeah, but suppose that um, if it is like n equals 3k, so that becomes 0. And if n equals, let's say, 6, yeah, it's a periodic signal, right? So it's yeah, it repeats every 3k. Yeah, so if suppose we try to find, let's say, x 0, then n equals 0. So here, yeah, we have to find, the 3k that equals 0, and it has a value of 1 here, right? So we can decompose this into several um, yeah, unit impulse to obtain this graph, and yeah, we can obtain this plot. If we want to find, let's say, x1, for example, this becomes, delta 1 minus 3k. So here, the value that could make this 0 is 1 minus 3k equals 0, and k is like 1/3, which is not possible, right? So yeah, we cannot get x1, so x1, therefore it would be 0. Same for x2, also same for x that's not multiply of 3. So if x is let's say 9, so we have like a x9, right? So sum the delta is 9 minus 3k. So for k equals 3, we have the value that's 1. Okay. Okay, now after finding the value here, after drawing the plot, we can also get AK. So AK here is the same as yeah, the same formula. So 1 over n, 1 over n, it's the sum from 0 to n minus 1, xn times e to the minus 4 of minus jk omega n. So in this case, we have the omega here is 3 because it repeats at every 3 time, right? So this is considered like one part of the signal, one period of the signal with period 3. So we can um, just plug in this value, right? And for n equals 0 up to n equals 2, which is easy to do because now we do not have this 1 and 2 because it's always 0, so it's basically just yeah, just like the xn, right? um, or it's just 1, right? 1 times e to the power of um, minus, yeah, jk, and it has a value only at time 0, so that would be times 0 here, so this is 1, and then we can obtain, yeah, this is just 1, right? So it becomes 1/3 for all k. So I think that's interesting that we see that this is basically a constant, like a constant of ak for all n. So n minus 7 until n minus 9, or actually, yeah, from minus infinity to infinity, the uh, value of ak is the same. It's 1/3 because the signal only, or the signals, the frequency of the signals is always 1/3, no matter where we are. Right. Right. So next, we are going to talk about some properties of the discrete Fourier series. So some of the properties that we have here, they are time shifting and linearity. So time shifting, if we have the discrete time signal, x, right? X shifted n steps, so x n minus m. Then if yn is x n minus m, then we have the value bk. So this is the coefficient of y. This they are actually, yeah, if we look at this, so bk is 1 over n times sum of the yn times e to the power of minus jk omega n. And if we plug in this value, phi, just the difference between n minus m, that would be phi plus m. So this entire thing here, this is ak. So this is, um, ak. And this is ak times e to the power of minus jk omega m. So we can get the relation between bk and ak. And then the next property that we discuss here is the linearity. So if we have two signals, xn and yn, where zn is the linear combination of those two signals. So zn, um, now what is ck? Ck is the Fourier coefficient of zn. If we plug in this value into this, so we get alpha xn plus beta yn times e to the minus jk omega n. And ck here is 1 over n times yeah, alpha xn. Also, we have 1 over n times beta yn. And we can get this ak, and this is the bk. We put this alpha and beta out, and we get this, yeah, value of alpha times ak plus beta times bk, right? So that's this is like ak. Of course, it's a alpha ak. Yeah. So this alpha will be pulled out, and we have ak, and this beta will be pulled out, and we have bk, and so on. All right, so the next property is called periodic convolution. So suppose we have Zn, which is the Xn. Uh, it's like a X with a circle. It's the notation here. So let's just say this is a periodic convolve. So xn convolved periodically with yn. So zn here, zn is sum of the ck times e to the power of jk omega n. And yeah, both of the signals are periodic. So both of the signals have uh, both of the signals xn and yn both have uh, Fourier series coefficient. So the Fourier series coefficient of xn is a, just say an and bn. So here it's written like a as and bk. Uh, denoting two different time unit. And turns out that the Fourier coefficient of Zn, which is ck, is actually n, the period times the ak, the Fourier coefficient of the signal xn, times bk, or the Fourier coefficient of the signal yn. So that's the relation between the um, two signals that form the signal Cn. N here is the period of period of Zn signal. Okay, so that's uh, how we have the relation between xn and yn. Both are periodic signal, and if they are both convolved, these two signals are convolved, it becomes Cn, and thus that becomes the Fourier coefficient could be represented by the multiplication between AK and BK and N. All right, so that's how it goes. Now, the regular convolution where the one of the signals are non-periodic or is non-periodic. So suppose that the one that's non-periodic here is the uh, impulse response Hn. If we have the periodic input Xn with Fourier coefficient of Ak, thus the output Xn star. So this is just a regular convolution or convolution uh, without periodic. One of the signals is not periodic. We just denote this by the regular star. So with only one Fourier coefficient, Fourier series coefficient, which is AK. So HM times AK times E to the J omega K, n minus M to the power of n minus M as well. So this one. Now, we can work on this. It becomes what's called like a transfer function. So this is the uh, Fourier series formed by the impulse response, which is non-periodic, but we form like the transfer function out of this Fourier um, of those impulse response. So Hm times e to the minus jk omega m equals to h k omega. And if we have the input, which is a periodic, then the output will have the uh, we'll have the Fourier coefficient b. The output is periodic, and b here, the relation is ak, the coefficient of the input, times h k omega, which is again formed by multiplying Hm here times e to the power of minus jk omega m. All right, so that's what's called convolution in the sense of the Fourier series. So the main point again is that the output of the convolution has Fourier coefficient bk, which is the Fourier coefficient of the input times the h of the the so-called like a transfer function. We will go into that later. Okay, so yeah, this is the related explanation here. Then we have yn. Yn is this e to the jk omega n times ak times sum of this. This is a transfer function. Is e to the jk omega n times ak times the transfer function. Yeah, so the input xn, the output would be yn, which is this, where we have this, right? So that's yeah, basically the just a little bit more explanation. It's actually the same as in the previous slide. So the next example, so this is for I think this is for linearity. Let's see. So xn is a cos pi n over 2. So cosine of pi n over 2. And it is a periodic signal with n equals 4. So why is that? Because if we have cos, yeah, like a cos pi over 2, right? So we have pi over 2 is like a 90 degree, right? So we have a cos pi over 2, we have a cos pi 2 pi over 2, we have cos 3 pi over 2, and we have cos 4 pi over 2, which is the same as cos 0, right? So yeah, that's pi over 2, and then also uh, yeah, 0, pi over 2, also like 3 pi per 2, then yeah, 2 pi. And yeah, you can see that this is the entire period, right? Um, the signal. So this is a periodic signal with n equals 4, and we can break this down into xn equals to half of e to the j pi over 2n plus e to the minus j pi over 2n. Then we can get the Fourier coefficient of one of this signal. So yeah, we have a1 equals half and a minus 1 as well as a minus or a3 is also half. And if yn equals to xn, so we are looking at this function yn equals to xn plus xn minus 5, then we can, yeah, so this is the let's say the time shifting part, so this is the time shifting part, and this is the yeah, summation of two signals. So the bk here is ak plus ak e to the power of minus j pi 5 pi over 2. Right? So if we go back to this time shifting, this is the time shifting and this is the linearity. So this example combine those two properties of the signal, right? So the next property is modulation. So modulation is the property if regarding the case of Zn, Zn equals to Xn times Yn. So Zn here is sum of this Ck times E to the Jk omega n. Both signals are periodic, Xn and Yn. So periodic with AK and B. Maybe it should be like a AN and BN, right? So that would be A K times BM times E to the J K E to the J K plus M omega n. So given S equals K plus M, so K and M is this, we can obtain this Zn equals double sum of A S minus M Pm E to the Js omega n. And this is considered xn, yn, so we have ck for the zn, for the signal zn. So say we have ck, and ck is actually the sum of this a k minus m b m, which is considered the periodic convolution of AK and BK. Right? So that's the modulation property. So if two signals are multiplied, both signals are periodic, which have their own Fourier series coefficient. Thus, the output signal Zn here has the coefficient Ck, which is the let's say like this is the periodic convolution of AK and BK, or the definition is like this: AK minus M times BM for M equals 0 until M equals N. And large, the capital N, is the period of Zn. Okay, so the last part of this class here is the discrete time systems with periodic input. And we can see here that a discrete time periodic signal could be represented in form of linear combination of complex exponential signals. So the output of a discrete time LTI system with impulse response Hn and the periodic input. So the input is periodic, the impulse response is not always periodic, or we commonly say that it is, or we commonly assume that it is not. And the output here is, yeah, we can see that this is the convolution, and we can see that this is how it goes for periodic input x. Yeah, so this is the periodic input x with the complex exponential, and that is the e to the j omega n. We just pull this out. And this is called the transfer function. So the one that you already knew before going into discrete time system. So yeah, this is more or less similar to the continuous time system, especially for the periodic signals, or the continuous periodic signals. Now we are going to do the same with discrete time periodic signals. And yeah, we have h omega, which is the sum of the hk impulse response times e to the minus j omega k. Yeah, so this is the capital omega. So h omega is the transfer function. Then the magnitude function is the absolute value of h omega, and the phase function here is the angle, or the phase of h omega itself. Now, if we have the discrete transfer function with h omega, then with input xn, periodic input, of course, with Fourier series coefficient ak, and thus the output would be the multiplication of those ak times h k omega. So we have the now Fourier series coefficient for the output, which is dk. And it turns out that dk is basically ak times the Fourier, or the transfer function h omega k. Okay, so this is the main point here. So let's look at some of the examples. So example 5 here, obtain the system response of yn plus yn minus 1 equals xn. Okay. So yn plus yn minus 1 equals xn, and xn itself is the periodic signal with Fourier coefficient ak. So yeah, we know the structure of the problem now. Xn having coefficient ak, and yn here, we try to find the um, coefficient on the transfer function h uh, omega k. Okay, sorry. So so h omega k, now could be factor this out. So this is the h omega k plus e to the minus jk omega times h omega k equals to 1. We kind of cross this out, right? So we kind of cross this out. Now we have h omega k is 1 plus 1 over 1 plus a e 1 over 1 plus e to the j omega k, and yn here is the sum of ak times e to the jk omega n times h omega k, which is so this is we didn't or we don't do anything with this. So h omega k, we just plug in this value, right? So that's the output. It may look a little bit abstract for now, but let's see for the next example. We get the output yn is ak times e to the jk omega n over 1 plus e to the minus j omega k. All right. Now, the next example, here we try to obtain the system response of yn minus half of yn minus 1 equals xn. Now we have the input cos pi half times n and zero initial condition. So we do the same with h omega k. Now we have the h omega here. Um, yeah, so the since the input signal is already in a concrete form, cos pi n over 2, um, whereas here it's a little bit abstract or a little bit general. Now, yeah, we get the um, yeah cos pi n over 2, and we can pull this e to the j omega n h theta h omega, sorry, minus half e to the j omega and minus 1 h omega, which is e to the j omega n. All right, so the input here is xn equals e to the j omega n, and the output here is e to the j omega n h omega. Well, yeah, note that here we, we just assume this, right? So this is not this yet. But we assume that, okay, we have a complex exponential input, and thus the output is also a complex exponential multiplied by the transfer function. So h omega is minus half times e to the minus j omega times h omega, which is 1. So h omega is the ratio 1 over 1 minus half, 1 over 1 minus half e to the minus j omega. And since xn is the input signal cos pi n over 2. Now we can look at this period or this periodic input signal, right? And we change the form into exponential, complex exponential form. So e to the j pi n, j pi n over 2, and minus j pi n over 2, and yn here is half times e to the j pi n over 2, and this is the, yeah, we just basically multiply this with this, right? So the omega is pi n over, or pi over 2, right? Yeah, and then so we have this yn. Now we can do some trigonometric operation to make this simpler, but actually this is already all right. This form is already all right, but if possible, yeah, just try to do like some trigonometric operation uh, from the fact that if we have, for example, e to the j omega, that would be like a e like a cos omega plus j sin omega something, which is, yeah, this yn. So this yn is 1 over 1.12 cos pi over 2n minus 63 over 4 degree. So Yeah, the difference with this is again, this is still a general form of the signal. Maybe you can call this an abstract form of the signal, but finally, for yeah, from this xn, we can also get yn, which is from the concept that we have here. We can have like a yn sum of dk, right? So dk is this. Yeah. Yeah, dk is ak, so in this case ak times h is the this, right? So this is the dk and this is the e to the jk omega n. Hmm. Whereas for this is the signal. Okay, this way. Yeah. So whereas here we do not look at the Fourier coefficient of this. Instead, we already yeah, change this into complex exponential, and from this we straight multiply y multiply h omega by xn. So we use this yeah, hn hk in this case. Yeah, yn is the sum of dk e to the jk omega n. Okay, so yeah, again, this is for periodic signals. So for non-periodic signals, we will use the Fourier transform, discrete time Fourier transform, which will be discussed in the next meeting. So in the next class. Okay, so yeah, don't forget to work on the exercise found in the myITS classroom. And yeah, if we have time, we may repeat this, some of the explanations in the class in our next meeting. All right, so I think that's all from me. Yeah, thank you, and I will see you next time. Thank you.